continue in section 7, and the first thing that we're going to look at in this video is the greatest integer function, which is a type of step function. Sometimes it's even called a floor function because it takes the value that's less than or equal to any given value of x that you plug in. So I try to draw these kind of like double line brackets here. F of x is equal to the greatest integer of x, and that's the way this is read, where the greatest integer is the greatest integer less than or equal to x. So if I said, what's the greatest integer of 1.7? Well, what's the greatest integer that's less than or equal to 1.7? It'd be 1. About 5.5. The greatest integer less than or equal to 5.5 would be 5. What's the greatest integer less than or equal to negative 4.2? It's not negative 4, that would be greater. It would be negative 5. So the graph is going to kind of be unusual in that you're going to get what looks like steps walking up from left to right. You can find this by creating a T-chart. I'm just going to get it started here by plugging in some values. I'm going to start at 0. The greatest integer of 0 is 0. The greatest integer of a half, well, that would be greatest integer less than or equal to a half would be 0. The greatest integer of a fourth would be 0. 3/4 would be 0. 0.99999 would be 0. It would be 0 until I get to 1. So I would represent that with an open circle at 1. The greatest integer of 1 is 1, because 1 is less than or equal to itself. The greatest integer of 1.1, 1.2, 1.3, 1.4, they're all going to be 1 until I get to 2. And then it's going to jump up here to 2. The greatest integer of 2 is 2. The greatest integer of 2.1, 2.2, 2.7, 2.99999 is 2. Until I get to here to the 3, it stops there and it jumps up to 3. And as you can see, this pattern is going to continue going on this way as well as this way. What's the greatest integer of negative 1? It'd be negative 1. What's the greatest integer of negative 0.9, negative 0.8, negative 0.7, negative 0.000001? Well, it's going to be negative 1 until I get to 0, and that's when it jumps up right there to 0 itself. And the pattern continues. And you can plug in values, but the pattern's going to continue here in this direction as well. And notice the filled in dots are on the left, the circles are on the right of these little bitty step line segments. I'm not doing a very good job of staying with this here. Here we go. That's why I use graph paper and a steady hand. And this is going to continue. And these steps are all going to be the same size, and they're all going to rise up. And they're just a bunch of constant functions here on limited domain. That's why it's very much like a multi-ruled function or a piecewise defined function. Now, this is a guy that you're going to see a lot. You're going to see him because of all the different possible applications and contradictions and other things, including stuff that we're going to be talking about still in this section to come. Greatest integer function. Learn it, live it, love it. Okay? Over here, an example, an application of a piecewise defined function. This is a retail store buys t-shirts from a manufacturer. The cost is $7.99 per shirt for anywhere from 1 to 100 shirts inclusive. So if you buy one shirt, it's $7.99. If you buy 100 shirts, they're at $7.99 a piece. Then the price is decreased to $6.99 per shirt, anything after. So if you buy 101 shirts, 200 shirts, 5,000 shirts, you're going to be paying $6.99 a shirt. You're going to write a piecewise defined function that expresses the cost, C of x, in dollars to buy x shirts. Well, we're going to let x represent, since we're going from 1 to 100 and we don't have 1.5 t-shirts, we're going to let x be an integer, a positive integer, natural number, because it represents the number of shirts. Oops, don't need that. So C of x is going to be a multi-ruled function or a piecewise defined function because if we buy 100 shirts or less, we're going to pay $7.99 per shirt. We're going to let x be the number of shirts, x t-shirts here. So it's going to be $7.99 per shirt for x, 1 less than or equal to x less than or equal to 100. But it's $6.99 a shirt if x is greater than 100. And again, x is a positive integer. and that would be my rule here that describes this application. Now, I'm just going to get started with a little bit about, some more about analyzing different curves and such. I drew what looks kind of like maybe some kind of a trapezoid over there, but I outlined part of my graph of my function here, f of x, y equals f of x. Some of it in red, some of it in blue, some of it in brown here. And the key values where it kind of changes over here in color are at A and at B, and of course down here at C. So if we look at this curve, we say the function is increasing, which means it rises from left to right, from 0 to A. A function is decreasing if it falls from left to right. That would be from B to C, the part here in brown. A function is constant if it's horizontal from left to right, and that would be from A to B here. Now what we need here is more of a mathematical definition of increasing, decreasing, and constant functions. And we'll be, of course, talking about increasing and decreasing functions in calculus. So it's good to get an idea of what we're going to be referring to later on, probably next year for most of you.